With the second part of the video. In this part, I want to show you the images that I've captured and the processes that I went through. This should hopefully be much more interesting than the previous one. So one of the first things we want to start with is making sure that the images that we collect from the disparity match match our expectations. So on the left and right here and here, we see the original images, the left and right images that were captured. I'm using a tool called Beyond Compare. I've used it in the past. I really like it a lot. So I've moved the images and the alignment, and from that I can see that the foreground is aligned, as you see right here. When I align the foreground and the business card, I think it is, lines up, I have an offset of -47. Now, if we align the background, which I'm doing right now, we get a offset of -19. So that gives us the values that we should expect to come out of the OpenCV function when it creates the disparity map. And kind of as I mentioned in the earlier video, the first kind of surprise is that that number is multiplied by 16. So the next step is to create the disparity map. The process that you guys requested in terms of scaling, once you do that, you get the image on the left, and in the data that you sent, there's a truth image captured in using a different method, and that's the image here on the left, and the image on the right is the one calculated by OpenCV and the source code I delivered. This tool Beyond Compares allows you to create a tolerance for how closely the images match. So if I set the tolerance to 0, you see the white regions down in the image below here. Those show you that the two match totally. Now, if I bump up the tolerance slightly to 1, then the areas in blue there match. And when I hit, this is a tolerance of 2, and so on. As I increase the tolerance, more and more of the image comes into view. So from this, I'm very confident that I produced the correct scaling. And that's pretty important in this application, I think. So from this point, now we have a good disparity map. There is one other step we want to create before we move on to capturing the 3D file, and that is to create a mask. So this is the mask I created to ignore values that are outside of the range or that are certain to be invalid. You can see how that's done in the code, but on the left here, one interesting thing is this black bar. The black bar, it comes from regions that this image 6 and image 2 didn't have in common, and that's expected. That's totally normal. Okay, so the next thing to look at is the 3D image that was created. This is a 3D image using MeshLab to render. So before we move on to the OpenGL portion of the project, we want to see, okay, what gets saved, is that valid? So this to me looks like a pretty reasonable interpretation of the values. I think it can be trusted to be accurate. I don't see anything here outside of the norm. And then, so that takes us to the last part. I used some code, as I mentioned before in the previous video. I used some other code to have a rendering framework to start with. And I loaded in the PLY file into the initial point cloud data. So let me pull that up. This is the Python code I was using to run it. And then now if I just click on run, it will come up here momentarily. It is not. There we go. So as you saw, it pops up, and this is kind of rotating it. It doesn't rotate super fast, but it'll come back in view there. Now, it's a lot easier to see from the from Mesh Lab that it is a correct rendering, but as the point cloud kind of rotates out of view, you do see that, okay, it is getting rendered in 3D. And that's it. I hope you enjoyed this presentation. I found it a very interesting project to work on, and I hope to be talking to you soon. Thanks. Bye.